Hi, in this video, we're going to talk about prior distributions for Bayesian factor analysis. Okay, so a viewer reached out to me and asked, hey, how do I work out the details of the prior distribution if I'm doing Bayesian factor analysis? Okay, well, that's a very, very good question. Now, I'm doing everything from the BayesFM package. Here is that. So this is the one that I'm most familiar with for this type of work. So that's the one I'm going to lean on. Now, remember that in factor analysis, we believe that there are some features under the hood about our subjects that we have recorded data of that we can't assess directly. And so in factor analysis, we'll have something, let's say, like maybe intelligence or mathematics ability. I cannot, no matter how hard I try, actually assess mathematics ability directly. But I can give questions that are related to mathematics ability and then, try and make an inference on the unseen, unmeasured directly at least, aspect of what we would call mathematics ability. Same thing with intelligence. Like we do not see intelligence in our evaluations and our tests. We see their performance on individual questions. And so there's a difference there. And so anytime that I believe that there is an under the hood unseen variable that's driving what I see in the data, it's a good time for factor analysis. Now, with Bayesian, what we're going to do, we're going to have just like any other Bayesian situation, we're going to have a prior distribution and we're going to have our data and we're going to combine that to get our posterior distribution. And we're going to focus on the priors here, specifically setting it up for the exploratory Bayesian factor analysis. All right, there's going to be two aspects to this. First one we're going to talk about is the number of factors and the number of variables that go into each factor. That's going to be the first part. Then the second part is going to be looking at the covariance correlation aspect between the factors. All right, so let's dig into it. First, let's talk about simulating the prior distribution of the number of latent factors. So we're going to use the simulation number of factors prior function within BayesFM to achieve this. So this is going to, and I'm copying and pasting from the help documentation a lot here. So if you don't know, if you missed something, you have trouble with it, hop right on over to the package to look it up. Almost everything is a copy and paste on this video. All right, so we're going to have some things that we're going to set up, prior to things getting going. Everything's going to depend on the prior parameters used for the distribution of the indicators and on the size of the model. So number of variables is the number of manifest variables, number of variables that we have in our data that are being driven by the factors. And then, so Kmax is going to be the maximum number of factors that we believe that it could reasonably be for our data. And NID is an identification restriction. This is the minimum number of observed columns of data dedicated to each factor. Okay. And so the simulation number of factors prior function is going to simulate the prior distribution of the number of latent factors for the models that fulfill the restriction on the number of manifest variables for each factor, and possibly none. That could happen. And then it's also going to work on the loadings for us. Now, we could have several or a single parameter for kappa. So we have several as a vector or a single scalar parameter, kappa, that is passed to the function to simulate the prior for different prior parameter values and comparing the results. There's going to be an accept-reject sampling scheme. So we're going to get a vector of probabilities that is drawn from a Dirichlet distribution with concentration parameter kappa. And the in-var manifest variables are randomly allocated to the Kmax latent factors. And so what's going to be happening is it's going to be doing a random number generation, and it's going to do an accept-reject process to say, hey, is this a good distribution to include If yes, keep it. If not, reject it. So if each latent factor has at least NID dedicated variables or no variables at all, the identification requirement is fulfilled and the draw is accepted. The number of factors loaded by at least NID manifest vegetables is returned as a draw from the prior distribution. Note that this function does not use the two-level prior distribution implemented in CFSHP. This is where manifest vegetables can be discarded from the model according to a given probability. Therefore, this function only helps to understand the prior distribution conditionality on all the manifest variables being included in the model. Now, what do we get back? Well, what we're going to end up getting is we're going to get a list of length equal to the number of parameters specified by kappa will be returned, where each element of the list contains number one in factors. So the number of factors is going to be a vector of integers of length equal to the number of accepted draws, and ACC is going to be the acceptance rate of the accept reject sampling scheme. Okay, so when I do this, in each individual run that I go, I can set up a multiple kappa on here. I only put in two. So here you can see that I'm only going to have two kappa on there. I picked one that's high and one that's low. I looked through the help documentation to see what was the highest value it gave, what was the lowest value it gave. And so I'm going to try 1/10 and 1 for the kappa. Now, number of variables, we're going to know that because we have our data to work with, or we know what we'll have in the future. And now we're going to say our maximum number of factors that we have and the minimum number of observed variables that connect to each factor. And then we're doing random number generation for accept reject, and we're going to have a number of repetitions on there. And so I'm going to go through a couple of examples, and so you can see what's going to happen. Now, as I work through this, when I do my simulations, notice I've got a try right there. There are parameter combinations that are not going to give us any output at all. And so when that happens, you know that the combination of values don't work out. Modify as you need to get through. And so we're going to run through all the combinations I have in the expand grid. So I'm going to have every single time, I'm going to say I have 15 observed variables. I want at most 5 or at most 10 factors. I want at least 1 or at least 3, depending on which one it is, observed variables going into each factor. All right, and so let's go ahead and run through this. I'm going to use the lapply function because remember, we want to avoid for loops in R. This is an easy way to get around it. And this code will throw errors off of what I've got, but I just skip right over it. And data science is very different than software development. Software development, there's an error, you slam on the brakes, airbags deploy, everything stops, you pull the fire alarm. In data science, we just go to a different model. Like, all right, that didn't work out, just skip it. I'm just going to the next one. I'm not going to spend my time trying to work out these details. All right, and so after I do that, I'm just to keep the list nice and organized, I'm going to set up the parameters that I have, and I'm going to put them into I'm going to concatenate them into a string with a space in between the parameters and put that as the name in the list. So here, this is an unnamed list at this point, and at this point, it's going to be a named list so I can trace things back nicely. And then I'm going to go through and remove all the times that it didn't work out for me. Okay, so now let's go ahead and take a look. I'm going to print the output, and we're going to print the name, print the output, and I'm going to give the summary and the plot. Unfortunately, RStudio didn't, or the R Markdown didn't put the plots where I want them, but it'll be all right. All right, so here I'm printing out the results. So I've got a sample from the prior distribution of the number of latent factors, all right, number of variables, maximum number of factors, minimum number of observed variables going into a factor, and the number of repetitions that we had. And I can just, here the print gives the same results, and it gives us this little information so that we could go through and, analyze some things. So I actually called that in the function or in the code. And so here I can compare the two different kappas. This is very nice. So we're saying that at most 5 factors is what I want on this individual run. Okay. And so we've got 2 different prior distributions on the number of factors. I can see that, here 2 looks like it would be the most frequent off of this prior, and 4 would be the most frequent on the other one. If I want uninformative prior, I want uniform distribution. And so here, I'm realistically gonna have a hard time trying to get exactly uniform off this. I would want approximately. So if I want uninformative prior, I want as close to uniform as I can get. The BayesFM package, for most of the implementations, you pass these parameters into the function when you fit your model, and it automatically takes care of the prior for us. We can use the simulation.nfac.prior function to get an understanding of like how the prior is going to look before I actually do the run manually. All right, now here is another one. So here I've changed it so that we have at most 10 factors. Okay, well, let's see what happens with that. Oh, something I forgot to say, the ACC, this is the acceptance rate. So this shows that up to round off, 100% of the iterations were accepted when we ran through this. And so now let's try it with 10 as the maximum. And so now we can see we have a very different distribution. And we can see that when kappa is equal to 1, we can see that things are more to the larger values. When kappa is 1/10, it's more to the lesser values. All right. All right, so let's keep it going. So now, we keep it going with, now I have a maximum of 5 factors. I say I have to have at least 3 variables, connected to a factor. And then I get a different distribution. And so I can play around with this and see, what works right for my project. And we can see here that not 100% were accepted. In fact, when kappa was equal to 1, we only had a 12.5% acceptance rate. That means that, that quite a few iterations went through that were just wasted iterations, something to be mindful of. All right, so now we can take a look. All right, now, when I did the expand grid code, I set it up so that there were 4 combinations. So all possible combinations of these were ran through. You'll notice that we don't have 3 and 10, or sorry, I should say 10 and 3. That's missing from there. That gave an error, and I just rolled right over it, which I think is a good thing to do in data science, because there's usually a good reason why it didn't work out. Even if you're not aware of the reason mathematically, there's probably a reason for it. Just bounce, go on to a different one. All right, and so we can look at the distributions. So, and it's very nice that we can see, the lower kappa has, favors less factors on this one. Once again, the lower kappa favors fewer factors. And, we see, a similar conclusion. The details are different, but we can see that on all 3 of these examples, the lesser kappa favored fewer factors. All right. Now, that was all about the number of factors for a factor analysis. And so, which is definitely super important. If I can't figure out the number of factors, really, I'm dead in the water when it comes to factor analysis. After that, though, once I figure that out, once I get nailed down what I want, then, well, I'm going to need to worry about the correlation matrix. I'm going to have to worry about the relationship between individual factors. All right, so how we're going to tackle this is that we're going to look at all the different factors from a correlation matrix point of view. And there are 2 potential probability distributions that we could use for this. And these are multivariate distributions, so these are complicated, but Fortunately, I don't have to do any pencil and paper mathematics on this. I just let R do the heavy lifting for me. All right, so the simulation R.prior function from the BayesFM package produces a sample of correlation matrices drawn from their prior distribution induced by the identified version of the factor model. Given the prior distribution specified on the corresponding covariance matrices of the factors in the expanded mode. All right, so there's going to be two distributions that we're going to consider. There's the Inverse-Wishart distribution. Here's its Wikipedia page. So this is a probability distribution defined on real value positive definite matrices. All right, so remember, correlation matrices are positive definite. We're assuming that that we have no redundancies in our factors. So if it was semi-definite, then we could have had redundancy. Here we are making the assumption that we're not doing anything dumb in our factor analysis, so it's positive definite. In Bayesian statistics, this is used as a conjugate prior of covariance matrices in a multivariate normal distribution. And here is the probability distribution function. Notice that that bold-faced X is a matrix. So it's not an individual value, it's a matrix itself. All right, so related to it, but a more generalized version of this is the Huang-Wand prior. Wang and Ward propose a prior distribution for the covariance matrix that uses a hierarchical Inverse-Wishart. This is a more flexible alternative to Inverse-Wishart distribution, and it retains conjugacy. The Huang-Wand prior distribution alleviates two limitations that we would have if we had Inverse-Wishart. First, the uncertainty in the diagonal variances of a covariance matrix that is Inverse-Wishart distributed is represented only with 1 degree of freedom parameter. And this might be too restrictive. So when it comes to the diagonal of the variances of that covariance matrix, the Inverse-Wishart only has 1 degree of freedom. And so a parameter, that is 1 degree of freedom parameter, which might not fit our situation. If I'm unsure and I don't know, honestly, I want the simpler model. I'm going to go Inverse-Wishart. But if from subject matter knowledge, I feel like I need to have more flexibility on this point, I want to use Huang-Wand. Now, also, furthermore, the Inverse-Wishart distribution imposes a dependency upon variance and correlation. Now, the Huang-Wand distribution still has a dependency, but it's not as strong of a dependency. And so that offers us a little bit more flexibility. Me personally, I would go with Inverse-Wishart for everything I've done because I haven't had any chance to have a model that was so complicated that I needed this level of flexibility, but this is a good tool in our tool belt. Now, the parameters for this, I've intended for these two sections to be different, but they're not. I'm going to keep it rolling. So number of latent factors, all right, definitely I need to know that before, when I'm coming in. So now this is considered a constant at this point in the project. That I've already identified the number of factors that I want, and now I'm looking at the covariance, the correlations between those factors. All right, new sub-zero, degrees of freedom of the Inverse-Wishart prior on the covariance matrix of the latent factors of the expanded model. So this is degrees of freedom of the Inverse-Wishart prior. And S sub-zero is either a scalar or a numeric vector equal to the length of Kmax. So this is a parameter of the Inverse-Wishart prior on the covariance matrix of the latent factors. Now, if Huang-Wand prior is true, this parameter is a scale parameter of the gamma hyperprior distribution on the individual scales. While if Huang-Wand is false, the diagonal elements of the scale matrix of the Inverse-Wishart prior on the covariance matrix in expanded form. And so here, we have Huang-Wand prior. It's going to be true or false, depending on which one we want to use. Now, number of repetitions is the number of repetitions for the Monte Carlo replicates. Verbose true will give me more output. I put it to false because I don't really want the additional information at this stage in the game. So the covariance matrices are sampled from the prior distribution in the expanded model and transformed to produce the corresponding correlation matrices. To compare several prior specifications, different values of the parameters can be specified. So nu sub 0, s sub 0. The function then simulates for each pair of these parameters. Nu sub 0 and s sub 0 should therefore be scalars or vectors of the same length. A list of length equal to the number of pairs of parameters is what we get for the output, where each element of the list is an array of dimension Kmax by nrep. And this contains the correlation matrices of the latent factor drawn from the prior. Okay, so when I do this, I can set up nu sub 0, s sub 0 as factors within each individual runs, and then I can run through this. I'm going to go through and show you some examples. I'm going to once again set Kmax equal to 5 or 10, just to show you the difference. This will be a known value at this point in the project. I know how many factors I want. I will use the previous simulations to figure out what the number of factors should be. And the Huang-Wand prior is either true or false. If it's false, I'm using Inverse-Wishart. If it's true, I'm using Huang-Wand. All right, and so we go through and we get the different values being set up. And these are varying over the different things that we can have for these 4 combinations. And now let's go ahead and look at the output. Once again, I'm going to set up the names of the list to be the parameters, and I'm going to print print the output from the function, print the summary, and then plot the results. And this is very different than what we had before. All right, so remember that we have Kmax and Huang-Wand prior is going to be the name. So we're saying 5 is the maximum number of factors, and false for Huang-Wand. Therefore, this is going to be an Inverse-Wishart. Here are the parameter values that were explored on this individual run. And now we can see that we have very different values. We're looking at the absolute value of the maximum correlation. All right, so what this does, remember that I have an entire matrix to work with that for this probability distribution. And as such, I can't really figure out everything. So we're only going to isolate down to 2 things to make it tractable for humans to interpret: maximum correlation and minimum eigenvalue. All right, so the maximum correlation, well, if I have a super large correlation, that shows I have redundancy in my factors, right? Well, that's not really what I want. But another way to measure that is with eigenvalue. So maximum correlation that only tells me about 2 factors at a time. Well, let's say that I have, less correlation between my columns, but they're linearly dependent. Correlation can't pick that up, or there are situations where correlation can't pick that up. We can look at the minimum eigenvalue to check this out. So the minimum eigenvalue, if this is close to 0, that's an indication that 1 or more of my factors are redundant. So if I have a large maximum correlation, I know that there's two factors that are redundant with each other. One is redundant, I could get rid of one of them. But in a multicollinearity aspect, correlation can't pick that up. So we're going to look at the minimum eigenvalue. And if I see that this is close to 0, that's an indication that I have a redundancy going on that's kind of hard to see. I could have like correlations could be relatively small, indicating a lack of redundancy, but then the minimum eigenvalue could be close to zero. And by eye, this can be very hard to catch. And so what I want to see low maximum correlation, and I want to see large minimum eigenvalue is what I prefer as I work through this. And you'll notice I've got I've got two variations going on for this. We have our mean, our median, standard deviation. We have all these summary statistics on what's going on. And each value of the eigenvalues is coming from a matrix. We have an entire matrix as our random variable for the simulation. And so now we can look at the maximum correlation. And so if I see it clumping up at 1, I know I have redundancy. Minimum eigenvalue, if it's clumping up at 0, I know I have redundancy. And so expect those to kind of give us similar information. Now, there will be cases, there are times that the correlation could be, relatively small, but the eigenvalue could be like, really, really small itself. And so, the eigenvalue gives us a multivariate look at like correlation in that manner. All right. And so here, now we're going to have a maximum of 10 factors and inverse Wishart. And so, we can just see our statistics, look at our summary of this, get an idea of what's going on, maximum correlation. I mean, a mean of 0.95. Here I've got a mean of 0.6. All right, I mean, 0.95, I mean, that's pretty high for an average of correlation, right? And minimum eigenvalue, look at that, boom. So both of these are indicating that I have a redundant factor in there, and I wouldn't want to use this as my prior. Look at that. Look at that. It's all clumped up close to 1, clumped up close to 0. This is, the red line is not the distribution that I would want for my prior. All right, well, let's keep it going. And so now I've got 0.62 and 0.5. Let's take a look. All right. So, this gives me the options to figure out like what would work best for my project, what is going on. And then we get another one. Look at that. Look at the red. I definitely would not want this combination of parameters going on for me. And then we have just output. This is just how the objects are stored in R, and it prints it just as part of the print that I requested. All right. So in summary, if I'm going to be doing factor analysis, I need to know the number of factors first and foremost, right? There's no way I can do factor analysis without knowing the number of factors. In exploratory factor analysis, I'm usually trying to figure out the number of factors I'm going to use. And in traditional factor analysis, I'm going to just be using the data to figure out what that is. It may be like principal component analysis or another form of factor analysis to figure out like what looks right. Well, when I have Bayesian, I'm going to have a Bayesian prior. I have prior beliefs that are going on, and I'm going to incorporate that into my model. After I have my prior on the number of factors, I'm going to have a prior distribution on the covariance between my factors. And that's going to be enough to completely manifest a Bayesian factor analysis. And so I take my prior distributions, I take my data, put them together, I get posterior, and that's what I use to actually make inference off of my data and my model. All right, I hope this has been helpful. Life is short. Do math.